Download this code from codegive.com, link in the description below. Recovering corrupted save files, a deep dive with code examples. Save files are the lifeblood of many games and applications. They represent hours of progress, carefully crafted worlds, and deeply invested characters. When a save file becomes corrupted, it can be a devastating experience. This tutorial will delve into the common causes of save file corruption, explore strategies for preventing it, and provide practical code examples, primarily in Python, for attempting recovery, including identifying corrupt data and potentially salvaging parts of your data. Understanding save file corruption. Save file corruption can stem from a variety of sources, each demanding a different approach to recovery. Here's a breakdown. Sudden power loss / system crash. This is a primary culprit. During the save process, data is being written to the storage medium. If the power is interrupted or the system crashes mid-write, the file might be incompletely written, leaving it in an inconsistent or unusable state. Hardware issues. Failing hard drives, SSDs, or even RAM can lead to write errors and corrupted data. Bad sectors on a hard drive can render parts of a file unreadable. Software bugs. Programming errors in the game or application can cause incorrect data to be written to the save file. This can manifest as data overflowing buffers, incorrect indexing, or logical errors during the save process. File system errors. Problems with the file system on the storage medium can also lead to corruption. External interference. Sometimes, even third-party programs or background processes can interfere with file writing, although this is less common. Malware. In rare cases, malware can intentionally corrupt files or disrupt the save process. User errors. Manually editing save files incorrectly, without understanding the file format, can lead to corruption. 2. Prevention is better than cure. While recovery is sometimes possible, prevention is always the best strategy. Here's how to minimize the risk of save file corruption. Use a UPS, uninterruptible power supply. This provides backup power in case of a power outage, allowing the system to shut down gracefully and complete any ongoing save operations. Regularly back up your save files. Create a backup strategy. This could involve manually copying save files to a different location, using cloud storage services, or employing specialized backup software. Automate this process whenever possible. Maintain your hardware. Regularly check the health of your hard drives or SSDs using diagnostic tools. Consider replacing aging hardware proactively. Keep your system updated. Install the latest operating system updates, drivers, and patches for your games and applications. These updates often include bug fixes that can address save file corruption issues. Avoid unnecessary programs during save operations. Close any resource-intensive applications before saving your game to minimize the risk of conflicts or resource contention. Check game/application documentation. Some games or applications have specific recommendations for preventing save file corruption, such as disabling certain features or avoiding specific actions during save operations. Use save file verification. If available, some games have built-in mechanisms to verify the integrity of save files. Use these whenever possible. Avoid manually editing save files unless you fully understand the format. If you must edit a save file, make a backup copy first and proceed with extreme caution. Use a hex editor or a dedicated save editor designed for the specific game, if available. 3. Analyzing a corrupted save file. The first step in attempting recovery is to understand the nature of the corruption. This involves identifying the file format. Is it a binary file, a text-based file, example XML, JSON, plain text, or a database file? Knowing the format is crucial for interpreting the data. Using a hex editor. A hex editor, like HXD, FRHED, or HexFind, allows you to view the raw bytes of the file. This can help you identify patterns, locate potentially corrupt sections, and compare the corrupted file to a known good copy, if you have one. Looking for common corruption patterns. Null bytes, 0x00. Large sections filled with null bytes might indicate a partially written file. Invalid characters. If the file is text-based, look for unexpected characters or sequences that violate the expected syntax. For example, in JSON, you might see mismatched brackets or invalid data types. Repeated patterns. Repetitive sequences of bytes could indicate a data corruption issue. Truncated data. The file might be shorter than expected, indicating that it was not fully written. Header corruption. The header of a file contains critical metadata. If the header is corrupted, the application may not be able to recognize the file. 4. Recovery strategies and code examples. Python. The recovery strategy depends heavily on the file format and the extent of the corruption. Here are some common approaches, with Python code examples to illustrate the concepts. A simple text-based files, example plain text, CSV. For plain text or CSV files, the corruption is often easier to identify and correct. Explanation. One file handling with encoding equals UTF-8, errors equals ignore. Crucial for handling various character encodings. The errors equals ignore allows the program to skip over bytes that can't be decoded, preventing it from crashing if it encounters unusual characters. Consider other error handling options like replace invalid characters with a replacement character, or surrogate escape, more advanced, preserves the original bytes as surrogate pairs. 2. Line-by-line comparison. Reads both the corrupted and backup files line by line. 3. Corruption detection. Basic checks for empty lines in the corrupted file as a simple indicator of corruption. You could expand this to check for other patterns, like lines with a specific length or lines that fail a simple validation check, example checking if a number is within a reasonable range. 4. Backup data replacement. If a line is considered corrupted, it's replaced with the corresponding line from the backup file. 5. Handling different file lengths. The code now gracefully handles cases where the backup file is longer than the corrupted file by appending the extra lines from the backup. 6. Error handling. Added comprehensive try, except blocks to catch file not found error and other exceptions during file reading and writing, preventing the script from crashing and providing more informative error messages. 7. Recovered file saving. Writes the recovered data to a new file with a .recovered.txt extension. Improvements. More sophisticated corruption detection. Implement more robust checks for corruption. This could involve checking for lines that deviate significantly from the expected pattern, validating data types, or using checksums, if available. Fuzzy matching. Instead of exact line matching, use fuzzy string matching, example using the difflib module in Python, to identify lines that are similar but have minor differences. This can help recover data even if the backup file is not an exact match. Data validation. If the file contains structured data, example numbers, dates, validate the data to ensure that it falls within reasonable ranges. JSON files. JSON, JavaScript Object Notation, is a common format for storing structured data. corruption in JSON files can be more challenging to fix. Explanation asterisk. 1. JSON parsing asterisk uses the JSON.load function to parse the JSON files. Handles JSON.json decode error if the file is invalid. 2. Recursive data comparison and recovery asterisk. The core of the recovery process is a recursive function compare_and_recover. This function compares the structure and data of the corrupted and backup JSON data recursively, element by element. Dictionaries asterisk. It iterates through the keys of the backup dictionary. If a key is missing in the corrupted dictionary, it adds the key and its corresponding value from the backup. If the key exists in both, it recursively calls compare_and_recover to compare the values associated with that key. Lists asterisk iterates through both list, calling compare_and_recover to compare each element and then handles different size by appending the missing elements. Primitive types asterisk. If the values are primitive types, strings, numbers, booleans, or their types differ, it simply replaces the corrupted value with the backup value. 3. Error handling asterisk includes try, except blocks to handle file errors and JSON decoding errors. The code checks if the loaded data is none, indicating a parsing failure. 4. JSON dumping asterisk uses JSON.dump, with indent equals 4 to write the recovered JSON data to a file, making it human readable. Improvements asterisk. More granular error detection asterisk. Instead of just catching JSON decode error, try to pinpoint the specific location and type of error within the JSON file. Schema validation if you have a JSON schema that defines the expected structure of your JSON data, use a schema validator, example using the JSON schema library in Python, to identify data that violates the schema. User-defined recovery logic allow the user to specify custom recovery logic for specific fields or data structures. This is useful if you have domain-specific knowledge about the data and how it should be recovered. Diff and patch use a diffing library to generate a patch file that describes the differences between the corrupted and backup files. This patch file can then be applied to the corrupted file to restore it to a working state. See binary files Binary files are the most challenging to recover because they lack the structure and readability of text-based formats. Explanation 1. Binary file handling opens the files in binary mode, RB for reading, WB for writing. 2. Header replacement replaces the header, the first header _size bytes, of the corrupted file with the header from the backup file. This is a common recovery technique for binary files where the header contains critical metadata. 3. Error handling includes try, except blocks for file handling errors. Improvements checksum validation if the binary file format includes checksums or other integrity checks, use them to identify corrupt blocks of data. Replace corrupt blocks with the corresponding blocks from the backup file. Data alignment be mindful of data alignment requirements. Some binary file formats require data to be aligned on specific byte boundaries, example 4-byte or 8-byte alignment. Incorrect alignment can lead to crashes or unexpected behavior. Reverse engineering the file format can be very helpful. This involves analyzing the structure of the file and identifying the purpose of different bytes or blocks of data. Tools like debuggers, disassemblers, and file format analyzers can be used for reverse engineering. This is often the only way to meaningfully recover a binary file if you do not have another very similar copy. Iterative recovery attempt to salvage as much data as possible even if the entire file cannot be recovered. Split the file into chunks, try to identify valid chunks, and write them to a new file. This approach is useful when dealing with large files where only a small portion is corrupted. Data carving. Use data carving techniques to search for specific data structures or file headers within the corrupted file. This can help you identify and extract valid data even if the file's overall structure is damaged. Advanced techniques. File carving. This technique involves scanning a disk or file for specific file headers and footers. It can be used to recover files that have been deleted or partially overwritten. Tools like Scalpel and Photoric are designed for file carving. Data recovery software. Commercial data recovery software, like Recuva, EaseUS Data Recovery Wizard, or RStudio, provides a user-friendly interface and advanced features for recovering data from corrupted or damaged storage media. These tools often use sophisticated algorithms to scan for lost files and reconstruct fragmented data. Forensic analysis. In extreme cases, you might need to consult with a forensic data recovery specialist. These experts have specialized tools and techniques for recovering data from severely damaged or corrupted storage devices. 6. Important considerations. Make a copy. Before attempting any recovery operations, always create a copy of the corrupted save file. This will protect the original file from further damage and allow you to experiment with different recovery techniques without risking the loss of your data. Write protect the source. If you suspect that the storage device is failing, write protect it to prevent further data loss. This can be done using hardware write blockers or software tools. Be patient. Save file recovery can be a time-consuming process. It may take hours or even days to analyze the file, identify the corruption, and implement a recovery strategy. Accept limitations. Not all save files can be recovered. In some cases, the damage is too severe, or the file format is too complex. Be prepared to accept that you might not be able to recover all of your data. Seek expert help. If you are not comfortable working with hex editors or programming languages, consider seeking help from a data recovery specialist or a knowledgeable friend. 7. Conclusion. Recovering corrupted save files is a challenging but sometimes possible task. Understanding the causes of corruption, implementing preventive measures, and employing appropriate recovery strategies are key to minimizing data loss. The code examples provided in this tutorial are a starting point for developing your own recovery tools and techniques. Remember to always back up your data regularly and to proceed with caution when attempting to recover corrupted files. Good luck.